Alrighty, so big data, it's important because most of the time, if you work for a company doing data science work, you're going to have a large amount of data, way more than you would have just on your local machine running a simple project. So some terms you kind of need to know are basically CPU, memory or RAM, and then storage, so solid state drive or hard drive, and network. And these are kind of in ascending or descending order in terms of speed. So CPU is going to be the fastest to write, followed by memory. Memory is 200 times slower than CPU though. And then storage, that's 15 times slower. And then lastly, network is 20 times slower than storage. So that's kind of the hierarchy. You basically want to run things memory or CPU, or in machine learning and neural networks, you'll actually be able to use your GPU, your graphics card, if you have one. So those are just kind of some topics you should know. Here's some links, additional stuff to check out. And then lastly here, the 3 V's of data. This was in the curriculum: volume, velocity, and variety. So basically the amount of data, how fast the data is generated, processed, and then also the variety of the data. Is it structured? Is it unstructured? So that's kind of an intro to big data. We'll move on to the Tools of Distributed Systems notebook here. These are just some of the frameworks and tools that are used most extensively when it comes to big data. So the big one and kind of the older one is Hadoop. You'll see this a lot, especially even on data science job postings. It's something you kind of want to at least be familiar with. It's kind of just a way to process things in a distributed way. So
Wait, they're outdated already?
What was that?
It is outdated already?
It's not necessarily outdated. It's just like it says here, it's considered old school. Spark is kind of the future. It's kind of the newer, prettier thing to use for distributed systems. So that's kind of why you learn PySpark. That's kind of the shiny new toy that a lot of people want to use. So it's better if you're familiar with that. And yeah, so you worked a little bit with that in the curriculum. Have you guys seen the phrase ETL, extract, transform, load?
Yeah.
That's especially for data engineering, extracting data, doing some manipulation on it, and then loading it into a database. It's basically what data engineers do all day long. And then here's kind of a nice table. I think this was in one of the lessons too, of just the different big tools you use for different things. So for visualization, I'd say the big one here is Tableau, if you have to pick one to kind of get familiar with. It's pretty nice. It lets you make really cool charts and visualizations and do some cool things, a lot more than you can do like in Excel, and a bit easier to use and to basically have other people look at than doing it in Python. So I'd check that out. And then for computation, definitely Spark is important. And then next here would probably be Hadoop. So maybe know a little bit about both of those. These others are not used as much. I think DigitalOcean is kind of on the rise though, so that might be another one to think about. For storage, Amazon is going to basically be #1. There's also Apache HBase as well. And then lastly, for distribution and data warehouses, Amazon again, Cassandra, you'll see a lot of that, but there's a lot in this space, Oracle as well. So those are kind of just the big names, the big players. It's good to at least be familiar with them, what they do. Odds are if you apply to a job and they use one of these, they'll teach you that. Most of the time data scientists don't have to know, how to use all of these tools. These fall more in line with like a data engineering role. But you definitely look a lot better if you do know a bit about these as well. So moving on then, we'll go to the MapReduce notebook. So this is a term you'll see a lot, so it's good to know what it means. Basically describes 2 different jobs, mapping and reducing, and it's used for clusters. So basically what it would do to count the words in, say, this list of words that we give it, it splits it up so line by line. And then each split is basically ran on a different processor or a different unit. And it counts up the number of instances of each word in that phrase. And then it kind of shuffles. So it kind of collects here. So all the giraffes end up on one, all the lions on this one, and then it can reduce and basically sum those up. So then it generates the word count. Instead of just going through, you know, word by word, it does this in this distributed way that's way, way faster. This is kind of a simple example, so it wouldn't really be faster for this, but when you're talking about like a giant data set going through millions of records, this speeds it up dramatically. And then here's just kind of a picture of the steps in it. You have the mapping, then the shuffling, followed by the reducing, and then you have the output. So basically being able to kind of explain briefly that picture and those steps would be good to know. And then here's just kind of a summary of what each of those steps do. So that is kind of a really brief walkthrough of some big data topics. Does anyone have any questions with these things in particular, or the PySpark stuff maybe?
Yeah, Matt, what is a map reduce? Like, what data set would you put into map reduce? Is it only text or anything?
It's mostly going to be text, or basically if you need to count things or aggregate things. You'll see it a lot for like language processing stuff. Yep. All right, we will go ahead and move on then to pipelines. So if we want to switch to that notebook here, this one I have an actual presentation for. All right, so pipelines are basically conveyor belts for machine learning. So you can throw in all the different steps you want to do, scaling your data, training different models, PCA. You can basically throw everything we've been learning into it, and it'll do it all for you in one go instead of doing it kind of step by step. So these are really important tools to be able to use. It's from sklearn, so we'll go ahead and just import that here. And wait a second for it to load. And then we're going to import a bunch of tools that we've used here. So we're going to use the iris data set at first, just as an example. We're going to get standard scalar, PCA, a couple regression classifiers, and then also grid search. So we'll run that as well. And then we're going to load our data. So this is that iris data set we used a lesson or two ago. It's basically different types of this variety of flower. It's a classification data set, so there's like 3 different classes of flowers, and I think 4 features, and we'll just take a look at it here. So we have the sepal length, sepal width, petal length, and petal width. And then the iris is our target variable. I think it's 0, 1, or 2 for the different classes. So there's a data set. We'll go ahead and do a train test split like usual so that we can check performance. And then this is going to start to set up our pipeline. So if we're going to want to try out multiple classifiers and compare their performance, we need a list of those classifiers. So here I basically create a list of 3 classifiers: logistic regression, SVC, and decision tree classifier, and just make sure they all have the same random state so that we can duplicate results. And then we're going to create parameter dictionaries. So this is going to be for grid search. So I make a dictionary for each of my classifiers. So for logistic regression, there's not very many parameters to tune, so I just did this C parameter here. For SVC, or an SVM classifier, there's a bit more, so I included a few different options. And then for decision trees, you know, there's a ton, so there's definitely more you could add, but there's just a few combinations to try out here. So we have a list, of dictionaries of parameters and in the same order as our classifiers. This is decision tree. So we'll run that. All right, so now we're going to do a for loop. We're going to go through that list of classifiers, zipping it with that list of parameter dictionaries so that each one lines up with its parameter dictionary. And then we're going to create an empty list for our pipelines and an empty list for our best classifiers found through the grid search for each type of classifier we're using. So in each go of the for loop for each classifier, we create a pipeline. So this is kind of the syntax you need to follow. You basically do pipeline, parentheses, and then you're going to pass in a list of the steps that you're going to do. So you need to give each step a name with a string here, so SCL for scalar. So we're going to standardize our data, scaling it here. Then we're going to basically shrink it down to 2 components through PCA. And then we're going to fit our classifier for each one. And then we're going to do a grid search. So we're going to use the parameter dictionaries that we created and basically iterate through those combinations to find the best set of parameters for each classifier. And then you go ahead and you fit the grid search here to your data. And then notice in here for the grid search, the estimator is our pipe. So you treat the pipeline as an estimator in this case. And then here we pass in the parameter grid, scoring, cross-validation, so on. So we fit the grid search, so it'll go through all those combinations. And then once it's done, we'll go ahead and grab the best estimator off of that. We'll also add our pipeline to our list of pipelines. And then we'll just print out which classifier we use, the best parameters, and then the train and test accuracy. So if we run this, it'll kind of go through. And here you can see logistic regression. These were the best parameters, train accuracy, test accuracy. And then kind of same thing for SVC and decision tree. So this is a small data set. It's pretty easy to classify. So we're going to see high performance here. But for a larger data set, doing it this way will give you, a better comparison. One model will do a lot better than the others usually. So this kind of lets you compare them all in an easy way without having, multiple cells, doing scaling in one step, then doing PCA, then doing a classifier. This kind of lets you do it all in one go, and you don't always have to do multiple classifiers. You could just pick one, like say I wanted to just do decision tree or random forest, and then I could just make one pipeline, do one grid search, and basically do all the fitting, train and test accuracy all in one cell in a matter of a few lines of code. So it really simplifies things, makes things a lot easier. And so that's pipelines. They're not that hard to implement. You can look at the documentation if you want to see a little bit more about how to set this up syntax-wise. But all you need to know is you pass in lists of tuples. So we have parentheses with 2 items separated by a comma. The first item is the name that we're going to give it. The second is the actual object, so the scalar here, the PCA. And I guess one last important thing, if you're doing the grid search, you'll notice each of these parameters has CLF with 2 underscores appended in front of the parameter name. That's referencing this name here. So each of our classifiers in the pipelines have the name CLF. So when you're using the grid search for the parameters, you need to tell it where these parameters go to. And you do that by saying the name of whatever piece of the pipeline, followed by 2 underscores, followed by the name of the parameter that you're changing. So that's kind of the most difficult thing really about setting them up. But yeah, so that's pipelines. So I have a pretty short activity here for you. This basically makes a pretty nasty data set. You'll notice scale set to none, so you might have to do some scaling on this one actually. You have a lot of features, a lot of samples, You kind of have to decide maybe which classifier might be best, given the number of features, number of samples. So yeah, your task is just to implement a pipeline and develop a model of best fit to this classification data. Any questions before we begin?
Yeah, Matt, can you repeat the CLF underscore thing? What you were saying?
Yep. So each piece of the pipeline, we give a name, as you can see in here. And if we're going to implement a grid search, we just have to specify the name of whatever piece we're referencing. So it's the classifier in each case that we're doing the grid search on. So you have to put the name that you give the piece that you're interested in, and then 2 underscores. And then the last part is just whatever the parameter's called, like normal. Because normally, you would just have like kernel, C, degree, and gamma. So like that would normally be how you do the grid search. You just have to add that first part when you're dealing with a pipeline.
Okay, cool. Thank you.
So Matt, the name within the tuple of pipeline, is it fixed? Like standard scalar, it has to be SCL, right?
I could do anything here.
Oh.
So change it. I could change it here. So like class, and then I would just have to change it in all of these. You'll see I'll get an error here if I don't change in the parameters. But yeah, you can pick anything. It's just kind of something that you'll be able to reference later on, because sometimes you have to reference part of the pipeline. Because I think, let's see, so let's do like pipelines. We'll get the first one and set that equal to pipe. And we can see what we can get off of that. So pipe dot, let's see. Get params maybe. Okay, so get params will basically tell you like all the stuff you did. It seems to be in reverse order. So like scalars at the bottom. Oh, and then there's steps within this too. So you can reference it that way too, depending on what you set the names as.
So
All
do you
right.
recommend doing this on like a normal, so just with the data and the quantity of data we have, or is this more for if, let's say, we deployed on like a cloud, some type of Python image, we would want to set up a pipeline for that?
Probably both. It just streamlines everything.
Okay.
Yeah, for both. It's a lot easier for other people to follow too if you just have it all in a pipeline.
Gotcha.
Yep. All right, All right, so we're gonna preview the Mod 5 project now. It's been deployed, so you should be able to access it on Learn now. We've kind of talked a little bit about what it's gonna be like and what you're gonna have to do for it. So we'll kind of go into it here. So for this project, you're going to be choosing your own data set for the first time. So that's kind of when you source one that you find interesting and one that you think is appropriate for the project. There's a couple requirements. The main one is that this is going to be a classification model that you're building. So your target variable needs to be either binary classification or multi-class classification. There's a bit of guidelines here for selecting a data set. So like I said, it needs to work. It needs to be sufficiently complex. We'll get into the constraints on that in a little bit here. And then you also don't want to pick a problem that's too complex. So it's going to be finding the right balance. As you can see with the data set that we're currently trying to fit to, large data sets can take a lot of time. So depending on your computational capabilities, you may need to limit the data set that you end up choosing. So this last part, bonus points if you can find data that you source yourself. So you can go back to the web scraping we did in earlier mods, or interacting with an API. I would strongly suggest going this route, because then your project's going to be very unique. There's a lot of data sets out there that are really cool, but have kind of been done a lot, and are kind of really popular. So I think the more original and the more, homemade you can kind of make your data set, the better it's going to look on your portfolio. So constraints for the data set, it can't be anything we've already worked with. So nothing we've done in any of the activities, study groups, or anything in the curriculum, something completely new. It needs to have at least 1,000 rows, so 1,000 data points, and it needs to have at least 10 features or 10 predictors before you do any kind of one-hot encoding. And the last part, I need to approve your data set basically before you start. So the first step is kind of define a data set. Either message me on Slack, explain what you want to do, send me a link to it, or try and set up a one-on-one. And hopefully you all noticed on Slack, my schedule's kind of tight these next couple weeks. So I have another instructor, Jeff, who's going to be helping out, filling in for like one-on-ones, project reviews, and also approving data sets. So you can check my calendar. If a time's not available, check his, and there should be one there. He's awesome. He'll be able to help you really narrow down, and he'll be able to tell you if the scope of your project is too big, too small, that kind of stuff. So yeah, the first thing is just to find a data set, come up with the problem you want to solve, your game plan, and then send it to me or Jeff and get it approved. And then you can start working on it. And so you kind of have two approaches. You can either do problem first or data first. So you can either find a cool source of data, develop a problem around it, or you can think of a problem that you really want to solve and then try to figure out how you can get the data for that. So we have some links here to some cool resources. We'll just briefly go through these. You'll see, that one did not work. So I think it's UCI data set. You'll see this a lot if you search for like cool data sets. A lot of them are kind of hard to work with. They're in like different data formats, but definitely still look through them. But this has a ton. You can sort it by classification. There's 366 here. And then it tells you how many rows and how many features as well. And then also what year it's from. So that's one option. Another is Kaggle. So you could either look at a current competition that's going on, and you could actually compete in it and have that be your project, or you can find an older competition or just a data set. There's a lot on here. You can do some searching for different topics. So that's another good option. There's a few more here, Airbnb, you could do something with that. I found this repo. This is public APIs. So this is a whole list, different categories of basically open APIs that you could collect data from. So depending on what direction you want to go, if you want to kind of source your own data, this could be really helpful for that. And yeah, those are kind of the best sources, and really just searching on Google, like cool classification data sets can kind of get you some links. You can maybe get some inspiration that way. And as usual, deliverables is going to be the same. You need your technical notebook, a README on your GitHub, a blog post, PowerPoint, and then a non-technical and technical presentation. And also for this project, you should kind of incorporate everything we've done so far. So you should start off with an EDA section, exploratory data analysis, really dig into your data set, show some graphs about what's going on, then kind of get into building your model and evaluating its performance. And then as always, include a future work section at the end. And then this rest of the stuff is kind of what you've seen before, make sure everything's organized, have like a table of contents, outline your methodology and processes and all of that. And that is kind of the Mod 5 project. Does anyone have any questions about what is being asked of you?
Yeah, Matt, how tied is this project to our capstone?
So this needs to be different from your capstone. So if you already have something in mind for your capstone, you need to do something different for this, just so you have some variety. And you can kind of think of this as like a warm-up to your capstone, since it's the first, original project. You're finding your own data, that kind of stuff. So it's kind of like a trial run for your capstone. Has anybody thought of an idea for theirs? Or found a cool data set that they want to share?
I have a use case from my work, but unfortunately that data can't be brought out of the environment. So we have a VPN protected environment because we are using some PII data, personal identification data. So I'm not sure if I can use that. So maybe I'll find some similar in the marketing field. That's what I'm thinking.
There might be a way for you to like obscure the data, like take out any kind of identifiers and still have like the raw data though. You might have to check with somebody at your job, but that could be an option.
Yeah.
I found an API that I am in the process of vetting right now. I'm really excited.
Topic or what kind of API is it?
It's about proteins and protein structure. It's through the database NCBI, which is where all of the medical journals and everything are published. Whenever you Google, like, for instance, coronavirus, it'll be one of the articles that pops up. And they have several different API libraries. So if you're interested in science, it's something that I would definitely check out. They have like 50 or 60 different APIs that you can pull from.
That sounds like a good one. Yeah, definitely try and find an API or do some kind of web scraping if you can. It will be a lot more impressive. Does anybody have like an area they know they want to work in? They just don't have a data set for it. Like, do you have specific, industry or something in mind?
And I'm trying to do a classification on stocks.
Okay, so like, what would you be predicting then?
Whether to buy or sell it.
Thank you. You can hear Walmart in the background. That's a great. Yeah, for stock data, you can definitely do a lot of sourcing yourself for that. There's, a lot of ways to get all that data down. What were you saying, Anuba?
I mean, like, I spoke to you about this. I wanted to do tie in basketball and sort of like roster management. I might just keep that for my capstone and do something a little similar. But I already started web scraping from NBA.com just to start like my data set.
Okay. Yeah, I'd say if that's like kind of your passion project, to save it for the capstone, just so you invest the most time into it.
Yeah.
So yeah, maybe pick something else for this one. But that's good. You kind of already started the web scraping.
I wanted to do something. I think I talked to you about this too. A Kaggle competition with some NFL data.
Mm-hmm. Yeah, I remember that one. That could be cool. Let's see, what was it, like an NFL?
NFL, that's the one.
This one.
Yeah, I got to change it, or I got to add some formula to turn it into a classifier. So instead of predicting the length of the run, predict whether it's a successful play or not.
Mm-hmm. Yeah, and that's a good point. If you have a data set that has, a continuous target, you can always bin it and, make different categories out of it. So you can always kind of convert a regression task into classification. And yeah, a Kaggle competition that's currently going, like this one, would be really cool, because then you can appear on the leaderboard.
This one's actually done. So.
Oh, this one's done? I thought it said 2 months ago.
2 months ago it finished.
Oh, okay. I thought it said 2 go. Well, I think you still would get on this. I'm not sure. Let's see. Oh no, this is the final standings. But you could, well, I guess you'd be changing the task a little bit. But if you did do one that's completed, you could kind of compare your score to whatever the final leaderboard ended up looking like. Let's see what their current competitions are. All right, active.
Is it fun?
All right, guys.
The competitions as our project?
What was that?
Is it okay if we do one of the competitions as our project? If we find a classification project or competition?
Yeah, yep, that would be fine.
All right, guys, I've got to hop off.
All right.
Bye, Beth.
Bye.
I'll show you guys what I ended up doing. Pet finder adoption. So projects were a little bit different when I did the program, but for one of my projects, I did this competition when it was live. Let me see if I can get to it. So it was this like pet adoption site in Malaysia, and it was basically predicting how quickly pets were going to be adopted from like all sorts of data, like their color, their age, all that kind of stuff. There was even like in the description, like the description of the pets, that kind of stuff too. So there's definitely a lot on Kaggle you can use. And you can always kind of, like Andrew's going to do, change what the data set was set up for. So going from regression to classification or something like that. All right, has anybody's model finished fitting?
No.
So then what are we learning about large data sets and grid search?
If you don't have a powerful computer, the pipeline doesn't do much.
I mean, it still does something. It just takes a lot longer. It's mostly with grid search. If you really cut down the number of parameters you're changing, it would increase in speed. You could also try like taking out the grid search and just see how quickly it normally fits.
Right.
Or start off really small, like only have like 2 different parameters it tries out, and then you can kind of increase depending on how long it takes. But this is like something you very well might run into with this project, and especially with your capstone. Like you might have to let your computer run for 20, 30 minutes, an hour, 2 hours. It kind of just depends. The best thing to do though is to kind of estimate how much time by running like a smaller portion of the data, or a smaller grid search, just so you know how long you can be expecting for it to run. Another option is to turn verbose on some of the models. So set verbose equal to true or 1. That will have it spit out a line for basically each model it fits. So then you can kind of track what it's doing and how far along it is. Another option is on certain classifiers like random forest. There is this parameter called n jobs. So this is the number of jobs it runs in parallel. So if your computer has multiple processors, it can kind of utilize more than one and speed things up. And as Jacob figured out, if you set it to -1, it actually will max out the number of processors that are appropriate for your machine. So setting it to -1 is an easy way to increase your speed a bit. And I guess while we're waiting, so I might have Brendan and Bonnie's group kind of explain what they did, because they actually included the PCA number of components in their grid search, which was kind of cool. So if one of you who has that wants to kind of just explain that a little bit.
Sure, I can go through it real quick.
All right.
So the main thing for us, like Matt said, was that we included the PCA in components as part of our params. So you can see here we did PCA in components because we knew we had 5,000 features. We tried a bunch of different numbers around there, 500, 1,000, 1,500, all the way up to 2,500. This more than likely, we think, is probably slowing down the whole process. There's a lot of permutations that has to go through. And then the other thing that we tried is we decided to go with a random forest because of the large data set as well. So we looked at trying different number of estimators here as one of the features we were doing for the grid search, or the parameters, and then the max leaf nodes as well to try for the different number of parameters, or try for the different parameters. We also had originally a logistic regression in here as well, but we kept getting thrown errors about maxing out the number of iterations in sklearn. So we removed that and just went with the random forest. And then from there, it really is pretty much the same thing as the example. The only thing is now, because you have the number of components set as the params here for the grid search, you just leave that blank instead of in components being set to a specific number. And that's currently still running. So we'll see how accurate of this random forest classifier we get out of this. I'll let you guys know on Slack or something.
Yeah, I was gonna say we're kind of at time here, so I think everyone should just leave running what they have, and then whenever it finishes, go ahead and post in Slack, how long it took and kind of what the results were, and that way we can compare, and we can talk about it more on Wednesday too, which Wednesday will kind of be office hours. We can talk about the project, finding a data set. You can come with like data set in mind, and I can kind of give you feedback there. It's up to you. So yeah. Alrighty. Does anyone have any questions before we go?
Matt, what's the actual due date of the project?
That is a good question. Let me double check that here. Let's see. I want to say it's the 12th of March, but let me double check.
Wait, really? I thought it's 20th.
20th, yes, it is the 20th. 12th would be really soon. Yep, so the due date is the 20th. That's a Friday, and that's when you need to submit the notebook and stuff by. So you could schedule your project reviews the week of the 23rd. So yeah, you have 2.5 weeks for this one. So, maybe by the end of the week, come up with your data set, and then you'll have 2 weeks to kind of do the actual project. That would be a good timeline.
Yeah, sounds good.
Alrighty, well, good luck finding a data set, and I'll see everyone Wednesday. Bye, guys.
Bye.
Bye.